Hey everyone, in this video we're going to talk about section 4.6b, which is about graphs of rational functions. Our last section should have been mostly review from Honors Algebra 2, and so within this section we are going to add on a couple of new concepts. So in example 1, we are going to describe the transformations of the following functions from the parent function y equals 1 over x, and then we're going to list all horizontal and vertical asymptotes. So when we're looking at describing our transformations, we're going to go back to what we did in Unit 1, and I can see that I have that written out right here. We're going to go through and describe what all is happening to our function. So our first one that we're looking at is 2 over x minus 5. So first, if I really wanted to, I could rewrite this as 2 times the quantity 1 over x minus 5. And that might help me see my transformations a little bit more. So first, when I have that 2 that's out in front, that's representing our vertical stretch or shrink. So we have a vertical stretch of 2. Okay, and then if I'm looking at my negative 5, I see that's really happening inside the argument, or it's happening to our x, and so what that means is that is going to be our horizontal shift. So we are shifting right by 5. Okay, and so what I'm thinking about is, based off of these different transformations, what is that doing and how is that affecting my parent function graph? So just as a reminder, our parent function graph 1 over x will look something like this. I'm going to have a vertical asymptote at 0 and a horizontal asymptote at 0 as well. And so my parent function graph looks like this. Okay, so if I'm vertically stretching by 2, all that means is that my y values are just getting stretched by that factor of 2. And so that's not really affecting any of my horizontal asymptotes because I don't have a shift. Where I do have a shift, though, is I'm shifting right 5. And so what that's going to do is that's going to take our vertical asymptote and it's going to scoot it over to x equals 5. So our horizontal asymptote should stay the same. Okay, I'm going to have a horizontal asymptote at y equals 0, okay, because that, again, it's just taking the function points and shifting them, and stretching them. I'm not shifting anything. But my vertical asymptote will be at x equals 5, because that vertical asymptote is getting shifted with all of the other points. Okay, looking at our second one, g of x is equal to 2x minus 1 over x plus 3. So when I'm comparing that to my parent function graph, there should be one thing that's popping out to you. And I know that you can't answer because you're watching a video, so you can't tell me what you're noticing. But one thing that I notice is that I have an x in 2 different places. Okay, I have an x and an x, whereas my parent function, I only have an x in the denominator. And so what that means is we need to rewrite our function in a different way, so that way I can really see my original parent function and transformations that have occurred to it. So you might be thinking to yourself, well, how are we going to do this? And the answer is going to be long division. Okay, it's one of our new skills and one of our new strategies to take some sort of rational function and to rewrite it into a new but equivalent form. Okay, so what I'm going to do is I'm going to take x plus 3, and I'm going to use that to divide into 2x minus 1. And so now we do our long division process. So I'm going to think to myself, what do I need to multiply x by to get me to 2x? And the answer is 2. So I'm going to multiply now both of my terms on my divisor. So I'm going to have 2x, and I'm going to have 6. Okay, I know I need to subtract those, so I'm going to change my signs. That does get rid of my x's, which is exactly what I want. And I'm left with negative 7. And now from there, we can't go on any further, okay? Because there's no polynomial term that I can multiply x by that's going to give me negative 7. And so what I'm going to have is I'm going to have this as my remainder. So rewriting this, I know I have my 2. Okay, that's what I have from here. And then if my remainder is 7, I'm going to do 2 minus 7 over x plus 3. Okay, that's going to be my rewritten version of this function. And from here, I can see a little bit better what my terms are going to be. So if I rewrite this again to kind of mimic what our normal transformations will look like, here's what we're going to have. Okay, so my negative and my 7 are going to represent out here. Okay, so negative 7. I'm going to have times a 1 over x plus 3. Great. And then I have my 2 that's on the outside. Well, that 2 is positive, and so I'm going to write it at the end. So here is a rewritten form of that rewritten form. And this is going to help me better visualize what my transformations are. So first, I see I have my -7, and I know that that represents kind of two different things. Okay, so first, the 7 represents a vertical stretch. So vertical stretch by 7. Okay, I know that that negative represents a reflection, and that's going to be a reflection over the x-axis. Okay, I see that my, let's get a new color, my +3, that's going to represent our horizontal shift, and it looks like we're going left 3 this time. So shift up 3. Okay, and then my +2 that I have is going to represent my vertical shift. Okay, so I'm going to shift up 2. Okay, so if we're thinking about the transformations that have occurred to the parent function and how that's going to affect our asymptotes, let's think about those. So my vertical stretch by 7, that's not going to change any of my my asymptotes. It's just going to stretch up my points from their original location. Okay, same thing though with that reflection over the x-axis. That just really shows or changes at least like what quadrant these are in, right? This is going to come up here. This would shift down here. Okay, so that doesn't really change any of the asymptotes itself. I think those shifts though are going to change those. So by shifting left 3, again, that's going to take where our vertical asymptote is, and so now it's going to move it to the left. So my new vertical asymptote is going to be at x equals -3. Okay, and then by shifting up 2, it's going to take where that horizontal asymptote is. It's going to shift it up 2. So my horizontal asymptote will now be at y equals 2. All right, so I think for right now, we are going to go ahead and we're going to skip example 2. We're going to come back to that in class, but I really want to focus in a little bit about what this example tells us before we go on to the next section. So one thing I just kind of want to point out is we could have figured out our vertical asymptote and our horizontal asymptote even without rewriting our function. Okay, the whole purpose of rewriting our function was to put it into a form where we could see those transformations a little bit more. Okay, specifically looking at the horizontal asymptote, I know what my horizontal asymptote is going to be, again, because of looking at my leading terms. Okay, so the degree of my numerator and the degree of my denominator matched, and so I knew that meant that my my horizontal asymptote had to be the ratio of the coefficients. Okay, so I knew that my horizontal asymptote was going to be equal to 2. Okay, it's similar to like how we knew in the first one that our horizontal asymptote was going to be 0, again, because the degree of my denominator was larger than the degree of my numerator, and so I knew, I knew that had to be y equals 0. But those were kind of just rules that were probably taught to you and not really explained why. But there's a larger reason as to like why we know that was going to be true. Okay. And we call this our end behavior model. So basically functions behave long term like the function families that result from the leading term of the numerator divided by the lead term of the denominator. Okay, and this is actually going to be a concept that we're going to delve way more into in the spring when we get to our calculus units. But we're looking long term at these functions to think about like what everything's telling us. So for instance, I have 4 different rational functions here. Okay, I want you to go ahead and pause the video, and I want you to predict what kind of end behavior they're going to have. And when I'm saying end behavior in terms of a rational function, I'm really talking about asymptotes. Okay, do we have a horizontal asymptote? If so, what kind? Or do we not have a horizontal asymptote? So I want you to go ahead and pause the video, and then we'll come back. All right, welcome back, everyone. So to take a look at this, let's go over it. Okay, so this first one, you probably said that this is going to have a horizontal asymptote. Okay, and that horizontal asymptote was going to be y equals 3/5. Okay, and you knew that because looking at my my leading coefficient, or my lead terms, the degree was the same, so it was going to be the ratio of the leading coefficients. Okay, for my second one, I see that my my numerator degree is higher than my denominator degree, so I don't really have a horizontal asymptote. I have something else, and that's what we're going to talk about a little bit more today. Okay, for my third one, Okay, I see that my lead terms, my denominator 1 is larger than my numerator 1. And when I'm saying 1, I'm talking about the degree. Okay, so that means that we do have a horizontal asymptote, but our horizontal asymptote is y equals 0. And then for our last one, again, the degree of my numerator is higher than the degree of my denominator, so I don't have a horizontal asymptote, I have something else, okay? And so let's look a little bit more closely at the graphs of these functions, okay? So first, I have that first one. We said that our horizontal asymptote was y equals 3/5. And so for an end behavior model, we want to think long-term about these functions, okay? I'm not just looking at, your -10 to +10 graph. I'm talking about what happens when I zoom way out. And so here we go. Okay, I have them graphed on Desmos. I'm gonna really zoom out. Okay, now look at the scale of my graph. Okay, that's pretty incredible. I've kind of lost a little bit of my scaling. Oh shoot, I didn't want to do that. Okay, I've lost a little bit of my scaling on this. And so if I wanted to, I could kind of adjust this a little bit on my y-axis. Okay, maybe let's go from 0 to, I don't know, 5. Okay, but when I do that, and I'm looking at my function, okay, if I'm zooming out long term, well, what does my graph look like? Okay, I've kind of lost that portion of my rational function that's in the middle, and as I'm zooming out, it really kind of just looks like I have some sort of line, okay? And so we knew that it was going to act like a horizontal line, and in fact, that horizontal line looks like it's 3/5, right? Like look at the scaling on that, okay? It's a little bit more than, in between 0 and 1, so 3/5 seems good. So long term, this is acting like a horizontal line. And we knew what that was going to be, that was our horizontal asymptote. Okay, let's look at our next one. So we said this one did not have a horizontal asymptote, but let's see long term what it looks like. Okay, so here's my rational function. Okay, doesn't really seem to fit some of our other ones. I know for sure it's not having a horizontal asymptote, but I'm gonna zoom out and let's look to see what happens to this. Okay, I'm zooming out. I'm going really far out. Well, what does it look like? To me, this kind of looks like a line. Okay, so long term, it looks like this function is no longer acting horizontal. It honestly looks like it's acting linear. Okay, let's look at our third one. Let's readjust. Okay, we again said that this was going to act, our horizontal asymptote was 0. So as I zoom out, what should we notice? Well, it looks like it's acting like a line. Okay, it looks like a horizontal line. And I'm going to adjust my scale just a little bit. So I'm going to go from 0 to, I don't know, 5. Okay, and to me, yeah, that looks like long term. Like this function looks like that horizontal line y equals 0. And so then let's look at our last one. Okay, we said it did not have a horizontal asymptote. In fact, look, this is a pretty weird rational function, okay? But as I zoom out, I don't know, what's it looking like? Well, let's adjust our scale a little bit. Let's adjust our x scale just a little bit. Let's go from -1,000 to +1,000. We'll go from 0 to 100. Looked like it was too much. 50, 500. Okay, well, this thing grows pretty quickly, so it's pretty skinny, but I don't know, to me, it's almost looking, it doesn't look like a line, it kind of looks quadratic. And so one thing that we can see is we can actually kind of predict long-term what kind of function families these are going to look like, okay, without even needing to look at the graph. So let's go back to our notes. Okay, so we know that we're looking at the end behavior of this by looking at the two leading terms of the numerator and the denominator. And so if I set up a ratio, okay, I have 3x squared over 5x squared. Well, if I reduce out this leading term, I end up getting 3/5. Okay, and so that shows me that this is going to act like a horizontal line. Oops, long term. Hopefully you wrote that down differently. Okay, we said that our second one was not a horizontal asymptote, but it looked like it acted linear. So again, let's take the ratio of those leading coefficients. Okay, if I reduce that, I'm going to reduce out 1x, and so it's going to act, so 5x is a linear function. Okay, so long term, this is going to act linear. Okay, again, our second one, our horizontal asymptote was y equals 0. Okay, if I take the ratio of the leading coefficient, or a ratio of the leading terms, I get left with 1 over x. And so again, that's not a horizontal line. In our calculus, our upcoming calculus days, we're going to do a little bit more of this. Okay, I'm thinking about, though, like as my x's get really, really big or really, really small, what's happening to this? Well, my denominator is getting either to be a really large positive number or a really large negative number. And if I divide 1 by that, I end up getting 0. So that's where that comes from. Okay, so again, long term, it's going to act horizontal. Okay, and then last, we said that was not a vertical or a horizontal asymptote. It acted like something else. I have x to the 5th over x cubed. Well, that reduces to be x squared, and so this tells me that long term, this is going to act like a quadratic. So this is what we're going to focus a little bit more. How do we graph functions where we long term don't act like a horizontal line? What happens if it acts linear, if it acts like something else? And I'll let you know that we're mainly going to stick to the linear cases because we're going to call these slant asymptotes. Okay, or we can also call this an oblique asymptote. The two of them are interchangeable. Oh, I looked this up so that way I had something. If it acts non-linear long-term, for instance, like this one acted quadratic, we can call that an asymptotic curve. We're not really going to focus in on those, but I want you to know, like, long-term, these rational functions don't always have to act like a line, okay? They can act other different ways. Now, one thing that I'm going to preface and say is that what we've discovered is that long-term, these are going to act like these other function families, but that doesn't necessarily mean that that is the specific equation of the line that they're going to act like. So for instance, this acts linear, it might not act like 5x. Okay, that's not necessarily the equation of our asymptote. Same thing here, it's going to act quadratic. That doesn't mean that the equation of that asymptote is x squared. So we need to do a little bit more work to figure out what that's going to be. And so I'm going to have you go ahead and flip over your page. We're going to look at an example. Hopefully this video is not too long, but I'm glad that you are sticking around for the ride. Okay, so here's the deal. So finding an oblique or a slant asymptote, again, that's going to be when it's specifically a linear, acts long-term linear. Okay, so first, that's only going to occur when the numerator degree is higher than the denominator degree. And we're going to use polynomial long division to find that asymptote equation. Okay, and the reason that we're going to use polynomial long division is because we know that by rewriting the function into a new form, it does have our asymptote stand out. I'm going to flip back one page, but we actually already saw this. Okay, in example 1b, when we went ahead and we rewrote our function using long division, we saw that the vertical shift was 2, and that meant that that was what our horizontal asymptote was doing. So using long division can rewrite it into a new form where we can see that asymptote stand out to us. So here's the example that we're going to look at. Okay, so we're going to sketch the function and list a bunch of features. So our function is f of x is equal to x squared minus 3x plus 2 over x minus 3. All right, so one thing that I do notice about this, and how I might start this off just like any of the other ones that we've been doing, is let's check to see if it can factor, because we do still need to find its intercepts, find discontinuities, find all sorts of stuff. We just know that in this case, since that numerator degree is higher than the denominator degree, we're gonna have to do a little bit of work to figure out like what the equation of that asymptote is. So number one, let's check to see if this can factor. And I think that we are in good luck because it does look like it does. So I think that numerator can factor to be x minus 2 times x minus 1. My denominator is just x minus 3. All right, so first things first, looking for intercepts. I do immediately notice that I don't have any repeating terms like within my numerator and denominator, so I don't have any holes, I don't have any of those removable discontinuities. And so what that means is that my two factors in my numerator are going to give me my zeros, okay? So that's good. So it looks like we have two x-intercepts. One's going to be at 2, 0. The other one's going to be at 1, 0. And then we do need to see if we can find our horizontal what was I going to say? Our y-intercept. Okay, and we know that we're going to find our y-intercept by plugging in 0 for x and solving for y. So choose a new color. Okay, so f of 0 is going to be 0 minus 2 times 0 minus 1 over 0 minus 3. Looks like that's going to be negative 2 times negative 1 is 2 over negative 3. So it looks like our y-intercept is negative 2/3. All right. Okay. Next thing that we're going to do, let's look for those discontinuities. Again, so we decided that there was no hole, there's no removable discontinuity. We do have a vertical asymptote though, okay, our vertical asymptote is going to be at x equals 3. And so remember, when we're talking about a discontinuity, I'm not calling it a vertical asymptote, I'm calling it an infinite discontinuity. And that occurs at x equals 3. All right, okay, here's where the fun begins. So the next thing that we're going to look at is we're going to find a horizontal asymptote. We know though, because we're smart, okay, we know that there's not going to be a horizontal asymptote, okay? So what we're going to do is we're going to use long division, and we might scribble this out. Okay, let's figure out what kind of asymptote it has. Let's use long division to figure out what our asymptote is going to be. So I'm going to come down below underneath my graph. So I'm going to take x minus 3. Okay, and I'm going to divide it into x squared minus 3x plus 2. Okay, so now we go through the long division process. Okay, so what do I need to multiply x by to get me x squared? That's going to be x. So x times x is x squared. X times negative 3 is negative 3x. Okay, I want to go ahead and subtract those, so I'm going to change both of the signs. And I do see that's actually going to get rid of both terms. Okay, so I'm actually just left with 0 here, but I do still need to bring down 0, 0. Okay, but I do need to bring down my other term. So I'm going to bring down 2 because that's all I had remaining. Okay, there's nothing that's a polynomial term that I can multiply x by to get me to 2, and so that's going to be my remainder. Okay, so I'm going to have plus 2 over x minus 3. Okay, so by rewriting my function, I'll do this up here. Okay, I've rewritten this, so I have this equal to x plus 2 over x minus 3. And so what I can see here is now I can see what my asymptote, my horizontal, not so horizontal asymptote is going to be. Okay, it's going to be this term here, x. Okay, and let's say that, for instance, it wasn't just x. Let's say that our long division had revealed this to be like x plus 3. For whatever reason, okay? Then our asymptote now would be x plus 3. And the reason why we're going to ignore this is, again, we're thinking long-term what's happening to x. As x gets really, really big, right? As we move this way on our graph, because my x values get really big, well, what's happening to this term? Okay, this term is going to act negligible because I'm going to have the denominator that's going to be so massive with either a really large positive number, if I'm going the other way, a really large negative number, but I'm dividing 2 by this number, and so long term that's going to be a negligible part of this. And so all that's really going to matter is what this value is here, okay? And so this is acting like x. So I don't have a horizontal asymptote, I'm going to have a slant or an oblique asymptote, okay? And the equation of that is going to be y equals x. Okay, and again, if that long division had revealed it to be x plus 3, it would be y equals x plus 3, but it's not. Okay, so it's just y equals x. So I'm going to keep that in mind for when I go to graph this. Let me get rid of all my scribblies. Okay, so I have all of this stuff now. Let's go ahead and let's try to start graphing our function. So I'm gonna go ahead and pause the video. I want you to go ahead and try to just graph as much stuff as you possibly can. When you're done, we'll go ahead and unpause and we'll check through a couple of things. One thing. All right, welcome back, everyone. Okay, so I have graphed the things that we said we were going to graph, and I also came up with a table of values of some other points. Okay, so what I have in my graph is all that we came up with just on the side of our intercepts, our discontinuities, and our asymptote. So when we go to graph our slant asymptote, and I didn't really explain this beforehand, wanted to see what you can do. Okay, but when you go to graph your slant asymptote, you're graphing that like you would any equation of the line. Okay, back to your Algebra 1 days. Okay, for this particular one, our y-intercept was 0 and our slope was 1, and so I graphed that line. Let's say, for instance, that it had been 2x minus 3. Well, now my y-intercept would have been negative 3, my slope would have been 2. So you're graphing that just like you would a line. Okay, I also came up with my table of values. Again, I just want to have a couple of points. My kind of rule of thumb is at least three around your asymptote, so that way you have something that you're graphing. So let's go ahead and plot those points. So I decided -1 was good, just so I could kind of see like what was happening. It is nice in that case because we do know that there are going to be some occasions where like you could cross your asymptote, your horizontal asymptote, your slant asymptote, and so that can occur sometimes. So sometimes looking to see if there's any points around where that's occurring is just kind of helpful. So at -1, I'm at -1.5, and I know this is super teeny tiny. There you go. Okay, we decided that when x was equal to 4, y was equal to 6, so I'm right here. Okay, when at 5, same thing, 6, and then when x is equal to 6, y is equal to like 20/3, that's like 6-ish. So, right, is it 6-ish? Yeah, we're not quite to 7. So here. All right, and so now we get to play that fun game of connect the dots. So when we go ahead and do this, I want to make sure that unless we've found any points where we're specifically crossing our asymptotes, I want to make sure that when I draw my line, I'm hugging my asymptotes. So for instance, it looks like out of my regions that I have, I'm kind of in that upper and that lower portion underneath where the intersection of our lines are. Okay, there could be times that we're to the left or to the right of it, but our points would have revealed themselves there, and so I don't think I'm going to have anything in those regions. So my line is going to look something like this here. Okay, and then over here, it's probably going to look something like this. Wow, beautiful. I love this for us. Okay. So now that we have at least a graph, we're going to come up with a couple of different intervals of increasing, decreasing, concave up, concave down, and then our function behavior. So increasing intervals, we're looking to see where we are going uphill. Now, here's the deal. When we went to make our graph, I do know that my increasing regions, oops, I should have put an arrow. Maybe there was one. Maybe there wasn't. Okay, my increasing regions are this region and this region. Okay, but what's the one thing that we don't really know about those regions that we would need? Well, I would need to know the exact x value where we have that local minimum and that local maximum, and I don't really exactly know where those are. Now, we would need something like a graphing calculator, Desmos, or in the future, calculus to help us figure out where those values are. Right now, though, let's just decide that x equals a is the local maximum, and x equals b is the location of the local minimum. Okay, and I'm just going to call those variables, so that way I'm still describing where I'm going to. I just don't really have the capability, unless we're going to use one of those other methods, to figure out the exact number where those are occurring. So I know that my increasing intervals in this case would be -infinity to a, and then b to positive infinity. Okay, that means that my decreasing intervals are going to be able to places that I didn't color in orange. Okay, so that's going to go from a to now. Okay, I'm going to that vertical asymptote, so a to 3. Okay, okay? And then again, I pick up on the other side of where I left off, okay? Again, I'm on the other side of my vertical asymptote of 3, and now I'm going to B, okay? Concave up and concave down is a little bit more easy to just pick up, okay? Concave up is going to be the top region here because it's concave up like a cup, okay? So that's going to be 3 to infinity. Oh my gosh, why do you keep erasing? 3 to infinity. And then concave down is the other region, so that's going to be negative infinity to 3. All right, okay, so now for our function behavior at the vertical asymptote and our end behavior statements, let's come into play here. So we know that we have a vertical asymptote. So we have some function behavior to discuss. So again, we're gonna do this in our limit notation. Okay, I'm gonna have the limit as x approaches 3 from the left. The same thing from the right. And then I can describe it just in general at that vertical asymptote. So if I'm looking at the left of my function, it looks like I'm going down to negative infinity. Okay, if I look on the right side of my function, looks like I'm going up to positive infinity. And since those don't match, I know that my limit at that vertical asymptote doesn't exist because they don't match. All right, okay, for our end behavior statements, okay, now I'm taking a look at what's happening as my function were to increase to the left or the right. So let's look at the right first. Okay, so as my x values get really big, what's gonna happen to my function? Well, it's gonna continue to go up, right? Like I have that arrow there. And so in this case, I'm gonna say that the limit as x approaches infinity of f of x, since my function is pointing up, it would continue to go up and up and up. I'm going to say that it is equal to infinity. Okay, I'm going to do the same thing now, but I'm going to go to the other side of my function. Okay, we're going to go to negative infinity. So as, let's switch colors. Okay, as my x values get really small, as they trend towards negative infinity, I see that the other side of my function is trending downward. Okay, so now we're going to negative infinity. And for right now, I would say that those are appropriate things to have. Now, we're going to talk again, a couple months when we enter into our calculus days, there are going to be some other ways that we can describe the end behavior. Saying that these don't exist is also going to be a reasonable thing for us to say. But for right now, because we're talking specifically just about like the end behavior, and we're talking about if the function is pointing up, pointing down, like where it's trending to, I would say that these would probably be the appropriate pre-calculus things to say. But I do want to kind of just give you a precursor that there's going to be a reason why we say that these eventually do not exist. So I have talked for far too long. We will do example 4 in class as well, so go ahead and just keep that one. Otherwise, that is all that I have for this